And then, without further ado, I want to introduce Christina Larkin. Christina's been with InPlanet now for 4 years. Is that right, Christina?
2 years, just
Two
over
years.
2 years. Yeah.
Right. Yeah. And, people at Vesta, we've been watching all the progress that you've been making there, with like super interest and so curious to learn from you today. And so I'll just turn it over to you. And if you have questions, feel free to put them in the chat, or if it's okay with Christina, just interrupt. And we'll try to save plenty of time at the end for lots of questions. I know I don't have a hard stop, so I can keep going at the end if people have questions. So, cool.
Sounds great. Thanks. And yeah, feel free to interrupt if you want. Happy to keep this informal. Can I just check? Can you see my slides? Okay.
Yep.
Perfect. And hopefully, yeah, this will not take the full hour. I think maybe 30, 40 minutes, and then we'll have a good chance for discussion too. So, yeah, thank you so much, Steve, for letting me speak today. I'm the Vice President of Science and Research at a startup called InPlanet, who are deploying enhanced rock weathering in Brazil. Before I begin, I just want to highlight that I work for a startup that is a remote first global company. We have a very diverse global workforce, and much of what I will present today was actually the result of a huge amount of teamwork. And although I have the privilege to be able to talk about it and our work, I want to acknowledge the hard work of the entire team who all contributed to this. It was by no means me that did all of this work. Um, just as a quick overview of my lecture today, I'll first start with a very brief introduction to enhanced weathering, as I know most of you here are familiar with it. I will then cover how InPlanet is viewing frameworks for measurement and monitoring of enhanced weathering in theory. I will then discuss InPlanet's approach, why we operate only in Brazil. And finally, I think the last part I'll spend the most time on, and I think will be of the most interest to us today. It's a case study where I will present some results from one of InPlanet's research trials that hopefully might spark some discussion, as it's data that we're still unpacking at the moment. And I thought it might be interesting for this group to look at it and discuss it. The first part of the talk focuses very much on the theory, and the last part, the case study, focuses on how this works in practice, with also a strong focus on the potential benefits and co-benefits of enhanced weathering with agriculture. I think we all know that to meet our climate mitigation targets, we need a wide portfolio of CDR, and we'll need a combination of both novel and conventional CDR techniques. Enhanced weathering, I think, is still widely viewed as a novel and emerging CDR technique, which may be cost-effective, scalable, with a high durability and high potential co-benefits. Enhanced weathering is typically simply the deployment of crushed reactive rocks, which weather to remove carbon from the atmosphere. We do this on agricultural land. We spread crushed rocks like basalt, but it can be deployed in other areas, like in coastal regions, like what Vesta does, and also even potentially in rivers directly. It's fundamentally the acceleration of a natural process that currently removes around zero point 0.3 to zero point 0.9 gigatons of carbon dioxide from the atmosphere every year via natural weathering of rocks exposed on Earth. Enhanced weathering is what we refer to as an open system pathway, meaning it happens out in the real world, in fields. Therefore, the MRV is challenging, and it is more challenging than compared with other CDR pathways. And I think we do have to acknowledge that. And there are also still plenty of open research questions, as well as some potential risks, and that does include environmental risks. But I personally think that regulation, safeguarding, and standardization can, will, and should mitigate those risks to ensure safe and effective scaling. If we do a very brief comparison to other potential carbon removal pathways, such as soil organic carbon storage and direct air capture, you can see why there's a lot of excitement and interest around enhanced weathering. As in theory, it's high durability, it makes use of existing infrastructure, and has a low energy demand, at least in comparison to something like direct air capture. If we use the byproducts from the mining industry, then it could also contribute to a circular economy. Enhanced weathering may also provide co-benefits to rural and low-income regions, and to much of the global south as well. So that's something just to bear in mind. Soil organic carbon storage, I think, has similar properties to enhanced weathering, but by comparison, a big difference is that it's a riskier removal in the sense that it has a lower durability and a higher chance of potential reversal. There is an additional context to enhanced weathering specifically deployed on agricultural lands, which I'll come back to later, but would like to highlight now. Is that a gap rock potters deployed with agriculture might be able to fill in addition to carbon dioxide removal is the potential to reduce the reliance on some amount of conventional fertilizers. And it may play a role in soil restoration, although I would say the extent and amount to which this is possible is still being studied. And it is also likely that there will be different responses under different soil, crop, and climates. And I think globally, tropical soils are extremely degraded. They have a very low fertility, and soil types like oxisols, which are the soils InPlanet primarily deploys on, is where the response and kind of nutrient response, plant response to rock powder addition is likely to be the highest and the most kind of beneficial area to deploy this. So that was a very brief introduction. I'm now going to move on to an overview of measurement and monitoring for enhanced weathering. This is just a framework for discussion, I guess. It's kind of how InPlanet is currently thinking about MRV for ERW and would happily kind of take any questions or thoughts from anyone here as well. Um, so to begin with, the measurement of CDR with enhanced weathering, I'm going to go back to the kind of definition of CDR, and then we'll juxtapose enhanced weathering monitoring onto this. So we define CDR as the removal or capture of CO2, which is then transported and stored durably. Net CDR accounts for the emissions when carrying out the removal and storage activity, the so-called life cycle analysis, or the emissions associated with the project. And these are subtracted from the carbon stored. Credit issuers also typically hold what they call a buffer pool, or a proportion of credits issued that are held back in the case of a failure or reversal. So in enhanced weathering, we consider the capture to have occurred via the transfer of carbon dioxide to dissolved bicarbonate. And this typically occurs in soils or rivers or coastal areas in the case of Vesta. In our case, transport happens via rivers and groundwaters, and typically the final storage location is in the ocean, where at this point we assume there is a minimal risk of reversal. Um, the emissions associated with our project occur on land and are quite easily measured directly. At each stage of this journey to get to a carbon credit, there are potential losses of CO2 post-capture but pre-storage that we have to account for. There are also uncertainties with the quantification at every stage that need to be propagated, which can be encompassed into a term I've put here, system-wide uncertainties. It's kind of this big term where it's basically all the uncertainties associated with every single measurement stage. And that can be accounted for using proper error propagation, conservative values, and crediting at lower uncertainty bounds in order to ensure that you've accounted for those uncertainties. But quantifying this kind of journey to an enhanced weathering credit is very complex. At some point, there must be a transition from a direct empirical measurement to a model or a calculation backed up potentially by literature data. And this is simply due to dilution of the signal downstream. You can never track one carbon atom or bicarbonate ion all the way to the ocean. So Cascade Climate, who you may be aware of, who are a nonprofit that standard sets kind of in the enhanced weathering space, defines these areas as the near field zone and the far field zone, where the near field zone can be measured directly, such as measurements of soils and pore waters. The far field zone, at least at the scale we operate at currently, cannot be directly measured, but it can be sort of calculated or modeled. Our LCA emissions are relatively straightforward for us to calculate, and we do that using primary data from mining, transport, and spreading. So measurement of enhanced weathering, I think, is underpinned by the classic silicate weathering equation, which I'm showing here, which is an idealized calcium-rich feldspar mineral reacting with CO2 dissolved in water to produce calcium dissolved bicarbonate, and then leaving behind a residue or a mobile fraction, in this case, a clay mineral. I think there are kind of three main ways people have tackled measurement of enhanced weathering at the field scale. I think the first is via direct measurements of changes in CO2 efflux. However, at least in our case, this is dominated by the organic carbon cycle because we have soils with vegetation. I think it's extremely difficult for us to disentangle the inorganic and organic carbon pathways. The second is via measurement of changes, measurement in the loss of cations from a feedstock in soil. And this is a solid phase measurement, which provides a time integrated indirect CDR kind of potential or weathering rate, and with some assumptions may be related back to CDR. I think this holds promise for a lot of suppliers because it can be integrated with current agronomic practices. You just need a soil sample. However, I think resolvability and soil heterogeneity really need to be taken into consideration, and it's actually can be quite challenging to get a signal out always using this kind of technique. The third measurement is via measurements of cations, DIC, and alkalinity directly in liquids phases, or some people are also deploying things like exchange resins buried in soils, which does a very similar thing. And this can provide a direct instantaneous measurement of carbon export at the location, time, and depth of sampling. It's the most direct measurement of CO2 removal. However, under some circumstances, it can be extremely difficult to implement at scale because we need semi-continuous measurement, we need to understand the wider hydrological conditions, and it's also extremely expensive to do at scale. At the moment, at least all methodologies that I'm aware of in enhanced weathering, you actually need a mixture of measurements. So you need a primary measurement as well as a validation measurement. So for example, you could credit on a solid phase measurement, but you also need a secondary validation, either via liquids or a gas measurement or an exchange resin measurement to back up so that there's a kind of redundancy in the measurements to ensure that you are seeing enhanced weathering and CO2 removal. So how do we integrate all of that theory kind of into practice and actually produce a CDR quantification? Well, we can put this into equations, which I've taken straight from the Isometric Protocol, who are a carbon removal registry that issue credits against which InPlanet credited at the end of last year when we issued the world's first enhanced rock weathering credits. So CDR is simply equal to CO2 that is stored minus the emissions associated with the project. So to calculate the CO2 stores, you could do this via a solid phase measurement. In this case, you would take the cation loss value that gives you the weathering rate, and then you've got to subtract all of the loss terms, so the cations that you might have lost to vegetation, to strong acid weathering, to those temporarily adsorbed on the adsorbed fraction in the soils, or those lost to secondary minerals in the soils as well. You also need to subtract any downstream losses, so riverine losses and marine losses as well. For a liquids phase measurement, at the depth of monitoring, you can directly measure the DIC export, but you also need to account for the far field losses in rivers and oceans, or you could even measure the cation export, accounting for any strong acid weathering, which will weather the rock powder but doesn't contribute to carbon dioxide removal. So currently, under the isometric protocol, you need both of these things to agree, at least within error, in order to issue any credits, just while we're learning more about these different measurement types and their error bars and what they mean. There is one loss term I'd like to just focus on very briefly, and these are the loss of cations adsorbed onto the exchange sites or soil particles in soils. For this term, the soil type you deploy on actually really matters because different soils have different capacities for holding cations, a bit like a sponge. So some soils have what we call high cation exchange capacity, such as very clay-rich, organic-rich soils, and some have a lower cation exchange capacity, like sandy soils. Also, acidic soils, which release acidity, may temporarily reverse carbon removal because they release acidity and then they cause degassing of CO2 by shifting the bicarbonate to CO2. And so, yeah, acidic soils will release acidity. And I think really the amount of acidity present in that soil will vary with the soil pH, but also the number of exchange sites you've got. Either, like sandy versus clay-rich soils have a different amount of acidity and a different buffering capacity. And I highlight this because tropical soils are typically very depleted in nutrients, but also are very acidic because of that. They have low soil pH. Cations have been leached from the soils under high rainfall conditions. Um, but I would also say that the total capacity to store cations and release acidity does vary depending on the overall clay organic matter and iron oxide content too. And therefore, this adsorbed loss fraction will be higher for some soils than other soil types. And you do have to be careful where you deploy, because you might be restoring the soils, but not necessarily leading to net CDR. Um,
Christina, can I ask a question there, if it's
Go for
okay?
it. Yeah.
I just want to make sure I've been trying to wrap my head around this because we haven't been thinking about cation exchange as much in the marine context. So the basic idea then would be that you've got a cation exchange site with like a proton stuck to it or a couple of protons stuck to it, and then you have like a swap of calcium in, two
Yes.
protons come off into solution, and so you turn that bicarb into carbonic acid, and
Correct. Yes.
that persists until the calcium kind of moves its way through the system.
Correct. Yes. So it's a temporary loss because
Yep.
eventually you'll end up with rainfall flushing the cations back out into solution. So it is temporary, but it will, at least at that time interval, lead to degassing of CO2,
Yep.
while you swap the hydrogen for
Yeah,
calcium and
everything
magnesium.
happens. Okay, cool. I'll have more questions about that later, but I'll let you keep going and then we'll chat later. Thanks.
No worries. But I think I would say that it's not necessarily a bad thing, you adding calcium to the exchange sites. In fact, it's restoring the soils. It's just not net instantaneous CDR, at least at that time.
I'm into that. If we precipitate a coral reef, everyone's like, "Aren't you losing the CO2?" I'm like, "Yeah, but we got a coral reef."
Yes, exactly. Yeah, yeah. And I also, yeah, this kind of relates to this slide quite nicely, actually. I want to highlight that not all loss terms, I would say, are created equal. Some are transient and some are permanent to semi-permanent. And so the adsorbed sink is typically temporary or transient. They're loosely bound cations and they'll eventually make their way into rivers and lead to carbon removal. And this is in contrast to like secondary mineral formation, which would be something like a cation-rich clay, and that's typically a permanent sink of cations. And at the moment, at least under current crediting methodologies, we are only accounting for the net instantaneous removal that occurred within a certain time frame, so an ex post credit of removal. And at that stage, some of the adsorbed fraction, it's accounted for, and it'll later be re-released, and you'll get back part of that credit at a later date. I would say the time frame over which this occurs is still an active and ongoing area of research. And I think, as we discussed, it's not a bad thing. Raising soil pH, filling cation exchange sites, restores nutrient depleted soils, particularly in the tropics. It improves them. And even if it doesn't lead to net removal within an accounting period, it probably eventually will. And so I think this is something that's a kind of an active, ongoing discussion across the enhanced weathering community about how we deal with that and how we deal with time accounting and time frames with enhanced weathering. So how do we fit this theory into practice at InPlanet? So here I'm just going to summarize how InPlanet is kind of currently viewing this measurement and the kind of approach that we're taking with our MRV. So in the near field zone, we determine weathering rates using immobile tracer methods by measuring the soils. We determine the biomass loss directly by measuring the plants. We look at soil losses, so particularly cation exchange capacity changes. Secondary mineral formation is something I would say that is still partly an open research question about how we can determine that accurately. It's kind of ongoing. We can have a look at things like soil inorganic carbon formation, but I think tracking secondary clay formation is something that's still very difficult to do quantitatively. We look at non-carbonic acid weathering losses. We do that by direct measurement, and also looking at fertilizer inputs and things like that. And we also have a secondary validation. So we're looking at direct liquids phase measurements, potential for new sensors, and also exchange resins as well could potentially also account for a secondary validation. We also measure the counterfactual weathering, so the weathering that would have happened if it weren't for rock powder being applied, and we do that via control areas that are actively monitored. In the far field zone, at the moment, we look at literature data and some very basic modeling to quantify what is likely to be lost during riverine transport. And the oceanic losses, we take a conservative discount based on a calculation using literature data from the ocean basin that our waters end up in. We also hold a buffer pool, which in the case of enhanced weathering are effectively surrendered credits because we can never know if a reversal happened because we can't monitor the reversals directly. Um, and then, yeah, the LCA, as discussed, is quite straightforward, and we do that based on primary data. And then we also, I should say, account for uncertainty at all stages. So we have to use conservative values or discounting, such as crediting. At the moment, we're crediting at one standard deviation below the mean in order to ensure that there's not a chance of over-crediting with enhanced weathering. And so to summarize this kind of section, I think I would like to emphasize kind of multiple and surplus measurements, at least at the moment, for the quantification of enhanced weathering. I think that all approaches have strengths and limitations, and that we need to kind of navigate uncertainty with excess measurement at the moment and addressing open research questions. And I think in terms of scalability, I think at the moment we're in quite a research intensive phase, data gathering intensive phase. And the way we view it, at least, is that this shift will come later on in a few years' time, hopefully, where we can reduce sample density, extrapolate more, model more in order to generate credits and maintain kind of heavily instrumented high areas of measurement at smaller scale. And that's kind of one way to get around dealing with needing a lot of measurements, but also needing to scale and make it cost effective as well. All right, I will now move on to discussing InPlanet specifically, our approach to science, what my team does, and then discuss kind of why we operate in Brazil, and also why Brazil actually, from a policy perspective, is a really interesting place to work for enhanced weathering, including a little bit about the legislation that we have in Brazil. Although in-field measurements are what we use to generate CDR credits, InPlanet is also committed to addressing a whole bunch of research fundamentals. And to do that, we've set up more than 10 different experiments across a range of scales to address outstanding research questions, study variability of enhanced weathering, and this is in addition to actively monitoring our current deployments. We're also committed to transparency and publication of our results um, as our data is generated. And yeah, and in particular, we've set up some multiple replicated block experiments that are directly embedded in commercial farms. And I'll share some data from one of those a little bit later on. In order to implement all of this, I do have a very large team of scientists, including many PhDs, that all work on MRV. And I'm very lucky to have a very diverse team that work across the globe. And we have expertise ranging from agronomy to geochemistry, modeling, geology, lab technicians, sort of everything. And most of them are actually based in Brazil because that's where all the work's happening, and they support all of the hard work on the ground. And like for us, this is kind of what's needed, at least at this stage, to implement MRV. Um, I also firmly believe that to enable the field as a whole, we have to be transparent about what we do. So yeah, we have a strong commitment to transparency. So we have a commitment to scientific publications. We've published one paper, have two in review at the moment, and more to come. We also share our data with the Cascade Climate data quarry, and I believe we were the first and still, I think, the only ERW company to make our commercial CDR data public, and to have shared it through this platform too. And I think it's important basically that we do that as a whole in order to enable the field and all learn kind of collectively as well. So why do we deploy in subtropical regions? I think most of us are technical experts here, but I do think it's worth a reminder that basically dissolution rates of feedstocks are governed by a number of factors, including mineralogy, grain size, reactive surface area, but also the conditions in the soil and water where the weathering is occurring. So dissolution rates are dependent on pH, water availability, and temperature. And so to understand rates of enhanced weathering under different conditions, I think we can learn a lot from natural basaltic weathering. And here I'm showing CO2 consumption as a function of runoff, which indicates basically that the fastest weathering rates occur at high runoff and also high temperatures too. And indeed, I think the fastest weathering rates on Earth occur on tropical ocean islands. And yeah, and I'm also showing here the temperature dependence of bicarbonate export. And again, with higher temperatures, we have higher bicarbonate concentrations in the waters. And fundamentally, that's kind of why we're targeting kind of tropical regions for enhanced weathering. And it's likely to be more efficient in tropical soils than in temperate regions. And I think just to highlight for reference, the kind of highest weathering rate observed on Earth, at least from this study, in a basaltic catchment, is equivalent to about 2.8 tons of CO2 per hectare per year equivalent. So it kind of just gives you a ballpark figure of what might be possible. At InPlanet, we operate in Brazil for a number of reasons, not least because of the readily available rock powder in local quarries. There's a huge amount of basalt, particularly in the south of Brazil, but also it presents us with quite optimal conditions for enhanced weathering. It's a large country, a lot of farmland, mineral depleted soils, tropical to subtropical climate, which should mean that we have faster weathering rates. In terms of operational emissions, these are actually lower in Brazil because it has a favorable energy mix powered by renewables. And it also has a favorable policy environment, as there's actually pre-existing Brazilian regulation around the use of rock powders or remineralizers, they're actually called in Brazil. And this means that rock powders are certified for use in agriculture, registered with the Ministry of Agriculture, and this regulation mandates requirements around heavy metal contents, cation and nutrient contents, and there's also actually a grain size restriction that means you can only deploy relatively fine-grained rock powders as well. As far as we're aware, this legislation is the first of its kind, and I think could be used as a starting point for further regulation in other countries. And this actually was implemented not for carbon removal purposes, but to encourage the use of alternative and more sustainable fertilizers within Brazil, because they import a lot of their fertilizers usually. And Brazil actually has a very long history of using rock powders and basaltic powders with agriculture, and it dates all the way back to the 1950s with the Russia Gem movement. And in fact, this year I attended the fifth Russia Gem Congress, which had several hundred attendees, and this was in July this year, and it was a congress all about the use of rock powders in agriculture. And although there's this sort of regulatory framework in place to support rock powder spreading as part of Brazil's national fertilizer plan, actually, what this schematic is showing is that this plan and the use of rock powders at the moment is currently on target to fall well short of what we would consider to be a climate relevant target. And actually, currently, less than 1% of agricultural land in Brazil use rock powders or remineralizers. And what that means is there's actually potential for deployment of enhanced weathering in Brazil to make a substantial and additional contribution towards climate targets beyond what would have been happening anyway with this shift towards sustainable fertilizer use. Um, and Brazil actually has a huge potential for deployment of carbon removal with agriculture. I think it has around 276 million hectares of land under management. About 160 hectares of that are pasture. And actually, my colleague Matthew Clarkson, who unfortunately couldn't make it today, but I know Steve, you know, recently submitted a really excellent review paper discussing how Brazil has the potential to provide a kind of positive societal tipping point for carbon removal via large-scale uptake of regenerative agriculture and enhanced rock weathering, if widespread adoption was incentivized. And you can check that out via the QR code here. Would highly recommend reading it, and hopefully that will be published soon as well. And there's actually a wealth of literature on the agronomic responses of crops to rock powder addition in Brazil, which we can draw on and learn from. Such that Phil Swoboda from my team compiled a meta-analysis of 54 Brazilian crop trials with what they call remineralizers or silicate agriminerals, they also call them. And that meta-analysis showed that the majority of the projects had significantly positive results with regard to key metrics like yield, above ground biomass, soil pH, and exchangeable cations. And that's something that's kind of very interesting for us to give kind of co-benefits to farmers as well. And you can check out the preprint as well via the QR code if you're interested. So I'll now journey to a real world deployment. And the last part of my talk will cover some of the evidence for the benefits or co-benefits of deploying enhanced rock weathering and also some data which might be of interest and spark some discussion. So this is a real world deployment on a farm in Brazil in Sao Paulo state from InPlanet. It's a sugarcane farm. And this picture is actually from our farm with the farmer Louise pictured. And here we deployed locally sourced basaltic powder on soils, which are sandy and heavily weathered, and so depleted in micro and macronutrients. You can see the orange color just at the bottom of the picture. The soils are very orange. It's very typical of tropical and subtropical soils that are very depleted with a lot of iron oxides. The soils are very low in organic carbon content, and the average soil pH at baseline was 5.9 across the whole farm. I think this is likely due to historic liming having raised the soil pH a little bit. Um, the climate conditions, I would say, are kind of solidly subtropical, so should be favorable for weathering rates. And this is also the site where we issued the world's first enhanced weathering credits. I will go into a little bit of detail about that today, but also want to highlight that all of that data is publicly available on the isometric platform, and you can reach the link via that QR code at the bottom. And I will also finish up this talk focusing on research coming out of the co-benefits from our research trial at this farm as well. So what did we do in practice for this project to issue credits? So just going back to the previous structure I introduced before, we measured the weathering rate using a paired or mobile tracer approach. We directly measured losses to soil and biomass. The soil losses were measured down to a depth of 40 centimeters in the soil. We also determined non-carbonic acid weathering, and all of this was subtracted from that weathering rate value. We also carried out a secondary validation with liquids, which was within error of the solid phase approach, albeit it was actually a lower estimate than what we had from the solid phase approach, but we credited on a lower uncertainty bound. So we credited at one standard deviation below the mean. We directly determined counterfactual weathering using a control site, and we also determined the oceanic and riverine losses, which were in total a 21% discount on the credits. And we held a 2% buffer pool, which were effectively surrendered credits as well. We took the full deduction from the life cycle analysis as well. And we accounted for uncertainty by doing uncertainty propagation, and we took conservative values at all cases in order to try and ensure that we wouldn't end up over-crediting. Our feedstock is a basalt, which we deployed at 10 tons per hectare across the deployment, with a maximum CDR potential of around 270 kilos per ton of rock powder. And it had a D50 grain size of around 120 microns, so it's quite fine-grained feedstock. The rock powder is certified for use with agriculture, with the heavy metals suitable and within regulatory limits, and so should be safe to deploy. The waters and therefore the inorganic carbon from this site drain into the Paraná River, which is one of the largest rivers in the world, actually. It's a roughly 5,000 kilometer long river. And the waters make their journey along the length of this river before they reach the final storage location in the South Atlantic Ocean. This river actually has one of the highest potential transport capacities for bicarbonate via enhanced weathering in the world. And this is primarily due to the dilute nature of the tropically and subtropically sourced waters. And it was estimated, at least via some modeling, that around 46 megatons of removal could be reached in this river basin before you ended up going over a threshold of saturation with respect to calcite and start precipitating calcite. So that's a fairly big potential capacity, at least for transport and export of bicarbonate. Our project site was in total 1,200 hectares, with 20% of the area being a control and 80% deployment. As kind of mentioned before, the baseline scenario here is sugarcane production with intensive management and fertilizer input, including ag lime usually being applied every 2 years. Our basalt was surface applied in this case, as the sugarcane is a perennial crop. And so there was no tilling of the basalt into the soil. Today, I'm now going to focus on some data coming from a research trial embedded within this commercial deployment. It's a site we've called our Field Monitoring Station, or FMS. And our field monitoring station is a multiple replicated block trial with n equals 4 replicates and 3 treatment rates, as well as controls. And we surface applied the rock powder at a rate of 10 tons per hectare, 50 tons per hectare, and 100 tons per hectare. And we sampled within each plot waters at 20 centimeter intervals all the way down to 1 meter, as well as soils were sampled all the way down to 1 meter. And we collected plant samples too. The soils were collected roughly every 6 months, and soil pore waters and gas phase measurements approximately every 2 weeks. We measured all of these parameters on those phases, and we also maintained an on-site weather station as well. So we're now going to dive into some data, which I'm still assessing, and I hope will be of some interest and maybe spark some discussion. I'm going to focus on the kind of agronomic soil data we collected at 6 month intervals at this site. And here you're looking at the 0 to 20 centimeter interval at the top and the 24 to 40 centimeter interval at the bottom. I'm showing the control on the left-hand side in white with increasing application rates at 10 tons, 50 tons, and 100 tons per hectare in the colored bars. These results are from our soil pH analysis, which I would say shows no real trend after 6 months. An increasing trend for pH after 12 months and 18 months, but only at the 0 to 20 centimeter interval, so not at depth. And this might be expected due to the fact that we surface applied the rock powder. We don't necessarily expect to see any trends below 20 centimeters. Um, the shift in pH at the 10 tons per hectare application rate after 18 months, so I don't know if you can see my mouse, but just here, so this shift is statistically significant, but not only statistically significant, it's actually agronomically relevant, and it's about a half a pH unit change roughly, which is pretty significant for the farmer and actually signals the potential to replace some lime usage. So that's quite an interesting result for us. For the exchangeable calcium, which is also what is plant available in the soil, the trends are far less clear. And I think we see no statistically significant differences. I think there's a slight increasing trend, maybe at 18 months at the shallower depth, but we see very little difference at deeper depths. For exchangeable magnesium, I think the shift is more apparent after 18 months of weathering at 0 to 20 centimeters. And we see an increase actually at all application rates that's statistically significant. Again, this is not translated to depth where we don't really see any changes at the 20 to 40 centimeter interval. For plant available phosphorus, this is the only nutrient parameter in the soil that follows a dose-dependent increase and a change at both the shallow and deeper depths. And this shift in plant available phosphorus is agronomically relevant. It's actually quite a large shift. And we did some back of the envelope calculations, and we realized that this shift actually likely exceeds the phosphorus released from the rock powder itself, which only contains a minor amount of phosphorus. And that's interesting. And our current working hypothesis here is that the silicon released from the rock powder might play a role in stabilizing plant available phosphorus. But I'm kind of open to ideas and discussions on that afterwards. But I do think this is quite an agronomically relevant result, and it signals the potential to replace some fertilizer usage for our farmers. We also measured estimated productivity at this site of the sugarcane at harvest. And we saw a roughly 34% increase in estimated productivity at the 10 tons per hectare application rate, which dropped at higher application rates, although it was not statistically significant. We did see a statistically significant increase in stalk diameter, so the physical thickness of the sugarcane stalks at the lower application rates, but not at the 100 tons per hectare. And so this kind of plant response is mirroring the non-linearity that we're seeing in the soil responses. So the soil pH showed a non-linear response, and the plants are kind of mirroring that, which is quite interesting. And it suggests that we're dropping off the kind of benefits at the higher application rates, and that the lower application rates are providing the most benefit. I I'm not showing it here, but we also see a similar trend with weathering rates, where actually the weathering rate at the lower application rates seems to be higher than at the higher application rates, which might be expected given that we're applying it at the surface and we have a kind of thick layer of basalt at 100 tons per hectare, which might cause some issues with kind of the dissolution kinetics at the surface.
How thick is that layer? I was trying to do the math quick.
Don't know, but it's visible. I can tell you that. I haven't done the maths, but it's like you can see it, whereas at 10 tons per hectare you can't see it. And so there's potentially some changes in like the surface albedo as well, because it's quite a dark layer too, and so it might cause drying and other issues as well. I would say that we also see at a different field monitoring station site with pasture a kind of similar trend. This is after 84 days, so it's still quite initial results, where we potentially are seeing something at the 10 tons per hectare, but not at 50 tons or 100 tons per hectare, which makes us think that this is potentially a real trend and that there's a dose-dependent response with basalt application rate. We also saw changes to production of sugarcane at the field scale, with an average yield increase of 6% between the control and treatment sites across this whole 1,200 hectare deployment. As sugarcane is a perennial crop, the yield declines each year with each cut. And we saw the highest yield increases occurring in the first and second year of the sugarcane crop. And we actually saw the largest yield increase between control and treatment for the youngest sugarcane, so in the first and second years, with a decline with a much smaller difference for the older sugarcane to actually almost no difference for the older sugarcane. We also observed an increase in calcium and magnesium content in the sugarcane stalks at the field scale, which suggests an increased plant uptake of cations too. So to summarize this section, we see the highest yield increase for the lowest application rates, and we see non-linear responses. We do see a positive increasing trend for many soil health parameters, including soil pH, but we have a dose-dependent response. And lower doses are typically yielding better results. We have an increase in plant available phosphorus, which may be an indirect effect via indirect silicon mobilization in tropical soils. And we do also see similar trends in other nutrient and micronutrient responses too. Um, and just to wrap up, to conclude kind of my whole talk, I would say that multiple surplus measurements are needed to quantify CDR with enhanced weathering and to provide kind of the necessary research to solve open questions. I think that regulatory frameworks such as what we have in Brazil can and should support safe and effective scaling, and that we need data transparency. We need discussions like this one today, publish our results as well, and allow for alignment across industry and academia in order to get this to a scale that's effective and can be a carbon dioxide removal solution at scale. And just before I finish up with questions, I think, Steve, you mentioned in your email, you put a number of links to kind of pieces and learnings and blog posts we put up on our website. And I would just say, yeah, this QR code will take you directly to our website. Please have a look, read them, reach out if you have any questions. I think we're always open to collaboration as well. And with that, I'll take any questions from anyone.
Thank you so much. That was excellent. Um, there's a question in the chat from Sylvia who asked if you got to analyze the effects on the soil microbiome.
Not yet, I think is the answer to that. It's something we're planning on doing, but we've not done it yet. Would love to because I think there's a whole bunch of research in Brazil actually around interactions of rock powder and microbiology, and that's something that we would love to get into, but we just haven't quite managed to get the analysis done yet.
Yeah, because that could explain some of these effects that you see that it was not dose dependent. I think you might have some explanations if you analyze that.
That makes sense.
Especially you are in Piracicaba, you have like the Exalc there, it's the biggest university already working with that. you can find some good people to do that there.
Yes, yeah, definitely we do. We've got a collaboration with Professor Andriace from Izalki, who I think works on this.
Perfect.
Um,
Yes, it's the best.
that makes sense. But yeah, thanks for bringing it up, and it's something that I'm definitely very interested in, and see if that might help us to understand. Yeah, maybe we're adversely affecting the soil microbiome, and that's why we are not seeing the same nutrient response and it's dropping off. Yeah.
Yeah, and it's quite a short time to see. I know the microbiome is responds fast, but it takes some adaptation for agriculture. So you might see an effect in a couple of years.
Yeah, I think that's a very valid point as well, for sure.
Gregor, I think you had your hand up next, and then Toby, and we'll get back to questions from the chat.
Yeah, thanks, Steve. Thanks, Christina, for this very interesting talk. I was wondering if you're measuring changes to the hydraulic properties of the soils and whether um, the benefits that you see being dropped at the highest rate could be related to changes in hydraulic conductivity, for example, because you mentioned, like, for example, albedo can also change that would affect water availability, increasing also other parameters like evapotranspiration and so on. So I was wondering if maybe there could be, let's say, a maximum application rate that would not disturb the hydraulic properties to an extent of making you lose those benefits.
Um, I think that's a really fantastic question and a really valid point. And I suspect that at the 100 tons per hectare rate, we are changing the soil structure and the hydraulic properties. I think the short answer is no. I don't think we've measured specifically hydraulic properties in every plot, just because they're quite small plots. And I think depending on the type of measurement, you need quite a lot of soils and big soil cores. So we do dig soil pits and measure the water retention curve and other properties of the soil. But we would do that kind of at baseline, separate to the trials. I think we probably need much bigger areas to do that accurately. At least my very basic understanding of that is that we would need a lot more space and to do that. We do measure the texture of the soil, so that actually is something I should probably look into a bit more. But I do suspect are right that that basically the hydraulic properties of the soil, they must be changing when you've added like quite that much rock powder. And then I think Steve, you calculated about a 6 millimeter thick layer. Like that's not an insignificant layer at the top. But I think it's a good point, and I would love to do more research into that and to take those measurements.
Yeah, I was wondering if it also might be affecting water availability for the plants, and these might be affecting their growth. So
Yes,
it could be related to that as well.
yes,
Yeah, thanks.
definitely. Yeah, yeah.
Toby?
Thanks for the talk, and thank you to Vesta for putting these on. They're really valuable community resource. This is more of a policy and philosophical question than a science question, but one thing that we struggle with when we think about enhanced weathering deployment in Brazil is feeding into a system that's driving massive land use change, and hugely carbon intensive system. How do you think about that? How do you guard against, your deployment contributing to that? And I think it's less of an issue with sugar cane than it is with soy and other crops, but would love to get your thoughts on that.
And by driving massive land use change, you mean specifically things like deforestation for agricultural use.
Yeah, or conversion of rangelands, but yeah.
Okay. Yeah, it's a good point. And I think for us we only deploy on areas that haven't undergone kind of recent deforestation. Like most of the areas in Sao Paulo state and the states we operate in have been agricultural land for a very long time. And so I think in that sense, we wouldn't be contributing to any deforestation and specific land use change for agriculture. I think by rangeland you mean conversion of like pasture into something like soy instead, because of as a direct result of us deploying enhanced rock weathering. I don't think we've seen that happen yet. And that actually isn't something that I'd considered that much. So I think that's a really good question. I will take that back to our operations team and think about that and how we can avoid any negative impacts there.
Cool. Yeah, it's something that's been in regenerative agriculture protocols for
Mm.
a while, and not in the current enhanced weathering protocols, but Puro and V2 just added a
Okay.
requirement that you can't deploy on recently converted land, and I think isometric will do the same. So hopefully it will be inserted into more of the infrastructure for the space, but just wanted to see what you guys were thinking about it. But thank you very much. It was really great. Thanks.
No worries, thanks. And I think it's a good point, and I've just made a note to look into that. But I would just like to stress that all of the lands we deploy on have, for a very long time, all been in agriculture. I think we don't deploy in any of the kind of Amazonia type recently deforested areas at all currently.
There's a couple of questions in the chat, and feel free to put your hand up or jump in verbally if you're on live. Robert Barrett asked, there's a gap in the dose from 10 tons per hectare to 50 tons per hectare. That gap is quite large. Is there any indication where the inflection might occur? So is like 15 tons or 20 tons better or worse than 10 tons?
It's a great question, and because of that, we actually changed our subsequent trials where we don't go up to 100 tons per hectare anymore, and we've done like 20, 60, no, 10, 20, and 60, I think we've done for one trial, where we're trying to close in that gap. This was the very first kind of commercial deployment field trial we set up, and I think from this we've changed our trials to try and figure out where the optimal dosage is and yeah, where that inflection point is. So it's a great question. It's something that hopefully our ongoing research will figure out.
There's a follow-up question there that asked whether there's any indication of transmission or uptake of minerals to plants that might impact regulatory acceptance.
I'm not sure if I understand the question.
Well,
Is it,
let me just, I mean, I was just curious.
yeah.
So you meant you were talking about pasture.
Yep.
Uh, and if there's any transmission from the mineral that you add to the pasture into the grasses that might then get taken up into the animal that are using it and that could potentially impact if there and again it really depends on what's in the minerals that you're adding, but just was one question that we had.
I think that makes sense. So I think primarily the risks are from like heavy metals like nickel and chromium would be the main ones. And basalts typically are quite low in those concentrations, at least compared to things like olivine, which Vesta's deploying up with, contain a bit more. I think there's still safe deployment rates to do it at, I should be clear, but in our case, we already start with a low amount of heavy metals. We deploy at a relatively low application rate, and we don't exceed soil thresholds for heavy metals, meaning that there's not really any chance that we will end up with them being transmitted into the plant and then into the animals. We also directly monitor this, so we measure the heavy metal content of the pasture grass, um, just to check. And so far, we've not seen any statistically significant difference in heavy metal uptake. But it is a good point, and it's something we have to kind of keep thinking about. But under the Brazilian regulation, they do regulate the content of the remineralizers that can be sold and used. So we should be covered under that legislation as well. But on top of that, we do all of our own monitoring just to be sure.
Thanks.
And Jordan, I don't know if you wanted to pop on, but there was a question that said the ocean losses are estimated at 21%. What are the efforts to constrain that, and what's the loss mechanism?
Perfect. So it's 1% for riverine losses and 20% for ocean losses. Typically, the main loss in the oceans is the conversion of bicarbonate to carbonate ions, so that chemical shift to higher pH in the oceans. And that's fairly well constrained with oceanic papers and equations that exist to constrain that. So I think that's fairly straightforward, and the main kind of loss mechanism in the ocean. In the rivers, there's kind of two main ways that we think you can lose a lot of carbon. One is if you end up going into a very acidic river downstream and you can drive degassing, or you reach saturation with respect to calcite and you precipitate out carbonate. Both of those things are very low in our system because we are nowhere near saturation with respect to calcite in the river, and also we check the pH downstream and we don't hit any really acidic regions. On average, it's a neutral pH. So actually, we put our riverine losses at 0, but we took a 1% conservative discount just to because there'll probably be some in there, but we didn't really see any major losses. Does that answer the question?
Yeah, I think so. This is a question I actually got from folks at Puro not too long ago too. It's not really a loss in the sense that like the I mean a fundamental understanding is that at pH 7, right, you've got 1 unit of alkalinity per 1 unit of bicarbonate
Yep.
ion, right? And then when you go into the ocean at pH 8.1, now you've got more carbonate ion, and every carbonate ion takes 2 units of alkalinity for 1 mole of carbon. And so it's just like you said, it's a respeciation. And
Yep.
sorry, Kristen, I don't mean to talk over you, but it's just a question that I've seen a lot too. And I'm keep trying to tell people like this isn't actually a loss. Like this is just the way the geochemistry works.
Yeah,
Um,
it's fundamental. Yeah, you're absolutely right. And no worries for you not talking over. I think it makes sense. And it's quite a difficult concept to explain, I think, sometimes. That it's just something that just happens in the oceans. And yeah. Yeah, no, maybe we shouldn't call it loss. Maybe we should call it something else, actually. I think that's a fair point.
um, hey, Gregor, did you want to follow up with another question? Oop, you muted.
Sorry. I was just wondering, as a follow-up to this last question, uh, and this might be a very naive non-geochemist question, but are there any, let's say, risks of losing carbon also in the groundwater sort of stage of your transit from field to river? Like what's happening in that sort of black box that we don't see?
It's a great question. I was a little bit cheeky actually by just putting up the river transport because of course there are a lot of storage in groundwater in Brazil as well. There's big groundwater aquifers. And that is something that is still, I would say, ongoing research from our side, but we have reasons to believe that the groundwater is quite stable. I think just based off of current chemistry measurements and bicarbonate concentrations in the basaltic aquifers that exist in Brazil, it's probably quite stable and it's probably quite stable for quite some time. But having said that, this is still an open research question and something that we definitely want to look into more. And yes, it might have the potential to increase the losses. Yeah, I think for sure.
Thanks.
Well, we're at the top of the hour here. Christina, I don't know if you're free to take questions or if you prefer to wrap up. We could do either.
Um, I can stay for probably 5, 10 minutes or so, probably 10 minutes, and then I probably need to go just to answer
Got
any
it?
further questions.
Yeah. I had a couple of questions if it's okay.
Go for
So I
it.
was curious. One is you actually at a couple of different points in your talk, you've talked about strong acids and the roles of strong acid weathering and acid rivers. Um, it actually seems to me like you're actually taking a discount there that maybe you don't need to take because those acids are going to flow out into the ocean. Like,
Yeah.
acid is acid and alkalinity is alkalinity. If you put that acid into the ocean, it's going to release CO2 or it's going to react with a limestone or something like that. So, what are your thoughts about that? And are you hoping to eventually reverse sort of that decision?
So yes, I think you've hit on something that is quite a big debate, I guess, amongst the community. And I would say that it's not me that's making the decision. It's kind of coming from the protocols with isometric. And you are absolutely correct. Like neutralizing strong acids is not a bad thing. It's a good thing. It could be potentially preventing degassing downstream. If it were to react with lime, it could have uh, released CO2 to the atmosphere. So neutralizing that with a silicate is a good thing. I think where it becomes a little bit tricky with carbon accounting is that's kind of an avoided emission rather than a removal. And I think that's where the definitions maybe need to be considered a little bit. And also you would have to show that in the counterfactual scenario, that would have led to degassing downstream and wouldn't have reacted with a silicate mineral, which it might have done. And so I think that's where it becomes a little bit tricky. For us at the moment, it's quite a minor discount, so it doesn't really have that big an impact, at least in the systems we're in. In some other systems, it might be much larger. So I would say I'm not saying one way or the other. I think it's a good thing. We're probably net being climate beneficial by neutralizing strong acids. It's just how and when you might be able to account for that in a kind of voluntary carbon market setting. I'm not sure. Would love your thoughts on that. And I would say it's still kind of an open discussion, and I think it's a fair point that you make.
Yeah, I'll back you up anytime. It's definitely going to dissolve a carbonate rock, and it's definitely going to release CO2. Um,
Okay.
um, I guess another question I had was about we had ZV Schaefer as a speaker a little while back, and she gave a great talk on um, weathering kimberlites and things like that. Um, in her talk, she showed that the year one rates were typically a lot faster than the year two rates, and that there was trace calcium carbonate that was dissolving and contributing to a lot of the year one rates, like, maybe like 1%. The rock might contain like 1% calcium carbonate, something that's like barely detectable by XRD. Um, do you think anything like that's going on in your system? Do you worry about rates slowing down over time? Um,
Yeah, definitely worry about rates slowing down over time. Because I think we definitely see the peak of like the faster dissolving minerals in the first year, and it will drop off. And so that's something, yeah, we're just heading into the second year of data from this project at field scale. I guess we're going to find out what that looks like. Pretty soon. In terms of trace carbonate, yes, I think that's absolutely something that can happen, especially in, less pristine basalts. There's probably going to be some trace carbonate present. I think we didn't really detect much of any trace carbonate in our rock powder, and we did do some like SEM analysis that didn't show any presence of carbonate, for example. And it's quite a pristine basalt, we think. So I would say, at least for the feedstock deployed here, we think it's unlikely. Um, at least to play a major role, but I think it is a good point, and I think you have to have a very careful feedstock selection. And one way to potentially get around the fact that you have carbonate dissolution maybe coming up first is you might have to just take a discount for the percent carbonate content in your rock powder. I think that would be a way to deal with that. But I think we think not, but happy to be challenged on that.
I don't know, just ZV saw it and I was curious. And then I have one last question or suggestion, and then I know you got to go. I'm curious if you thought about this cation exchange process and how that might propagate from a soil into deeper soil through the groundwater. I mean, that could potentially be quite a long process. Um, and it's like an infinitely long cation column that you could sit there and pipette acid into forever. Um, the and I guess have there been efforts to use, are there tracers we can use, like comparing like tritium or C14 to CFCs, or are there other like are there sort of geochemical tools we can use to get at the time scale that this signal might propagate through the soil and groundwater to actually get to a river?
I mean, I've not done it, but that's a great idea. I'd say for sure that I'm not aware, at least. If you are aware of any studies, please send them
I'm
to me.
not. I'm shooting from the hip
Um,
here, and
yeah.
I've been racking my brain during your talk trying to think about like what would make a good tracer versus a bad tracer. But yeah,
But
yeah,
I think something like that, like some kind of tracer that you can use to follow the process through the column so that you know when it's come out would be yeah, of a lot of interest. I think in Brazil we've got very thick, heavily developed soils where it's going to take a very long time for that to propagate. I don't think we need to, yeah, it will. And I think that's fair. I think the at some point, I guess something we discussed a lot is that I guess at some point at a certain depth in the soil, you're probably cut off from the atmosphere, which means if you do have any exchange below a certain depth, you're probably not going to lose the CO2 back to the atmosphere, and then eventually it'll make its way through. So I guess for us, we were kind of considering maybe there's like a cutoff depth at which it doesn't matter so much and you don't need to monitor. But yeah, no, I agree. And I think the timescale issue is one that's still a very big open question. And I think soils will take a long time to filter those products through and before they eventually make it out.
I'd love to shoot the bull with you sometime and dream up ways of tracking that. That's
Yeah.
the kind of geochemistry problem that I'm like, oh, that's juicy and fun.
Yeah.
So, and it probably looks a lot more fun when It's not between you and your funding. But so, all right. Well, thank you very much. If anybody else has dying questions, I guess we can reach out by email or something like that. And thank you so very much for a few extra minutes of your time, Christina. This was just fantastic, and you did such a great job. So really appreciate it. And we look to you guys as leaders in the field, and we know you're doing all the hard work and doing it all right. So appreciate it so much.
No worries. Thank you so much for having me. This was a lot of fun. If anyone on here wants to reach out with any questions via email, more than happy to have a chat. Even if it's a spicy question, happy to discuss it. I think it's important that we discuss these topics openly. So yeah, no, thanks a lot.
Yeah. Have a good day. Bye bye.
Thanks. Bye.